In this video, we're going to talk about the SPD, how to dump it, edit it, and get it back to the chip. Now, this video is mostly like part 2 of a video where I changed the chips on a DIMM, or upgrade the chips on a DIMM, and to make that work. But if you want to modify your SPDs, say timings or XMP profile or something like that, this is also relevant to you. Now, what is an SPD? SPD stands for Serial Presence Detect, and it's basically the digital equivalent of this sticker here. It contains information such as manufacturer, what kind of memory is it? Is it DDR2? Is it DDR3? Buffered, unbuffered? Stuff like that. It's not a program in like if, else, switch cases, stuff like that. It's really just a file where the BIOS, or later on in the boot process, the operating system, looks the information up. All this information lives in this chip here. It's an EEPROM, and they are, or how it's made up and everything is defined by JEDEC. JEDEC is an industry organization that basically standardizes, amongst others, but the SPD and how it works, how it's made up, the lookup tables and everything of that sort. And we want to change a few or quite a lot of details in that when we upgrade the memory chips on a DIMM. We want to change the density, obviously, of the chips. We want to change timings, because I upgraded from 1300 to 1600 mega transfers. We also can change manufacturer, we can change the part number, serial number, timings, yeah, quite a lot.
Now I want to have a look at how the SPD file is actually built, or how does it look. And you can see here is the initial dump of before I started upgrading it. This is the 2 gigabytes Kingston stick. As you can see here, it's basically twofold. Yeah, the upper red part is more information about the stick itself, whereas the lower part is serial number, part numbers, manufacturer, manufacturing date, and the XMP profile. And if we have a look at the upper part, the first 4 bytes are SPD information and memory type. So here we have like what revision does the SPD use, what memory is it, so DDR2, 3, and so on. Now the following 5 bytes are module organization and density and voltage. And here we can define stuff like how many banks does the stick have, how many ranks, what is the density of each chip, what voltage does it operate, so is it a 1.25, 3.5 or a 1.5 volt stick. After that we have quite a large chunk that's dedicated to memory timings. These timings are chip specific, and we have a look a little bit later on how to configure them. We make quite a jump. This is the general information, and as you can remember, this is in the red part of the SPD. So this is actually user changeable even on most stick, even if they are software write protected. This contains information such as serial number, part numbers, when was it manufactured, where was it manufactured, what chips is the stick equipped with. After that, in this case, this is blank because this Kingston stick didn't have an XMP profile, but here would be the XMP information. If you don't want to use that, you can zero it out like it's here. Otherwise, there are quite a few tools that can generate XMP profiles for you. Now, how to get these dumps? Well, basically we have 2 options. Or rather, to dump the SPD is very easy. The easiest one would be either one of those 2, either Thaiphoon Burner or SPD-reader-Writer. Both of these applications have their advantages and disadvantages, and I will have a look at that a little bit later on. I will start with the SPD-reader-Writer, and this is from a user called A213M from the EVGA's forum, and this software is basically twofold. We have on the one hand an Arduino flashing device, Although with the latest update, there is the option to flash it from your main board, so you don't need an additional hardware. However, that comes at a cost. And this cost is that you won't be able to circumvent the write protection. But if you want to write to and from a DDR3 SPD, this is very, very cool because it's much faster than having to solder on the wires and everything with the Arduino flashing device. But you need to have one of those supported chipsets. Unfortunately, my X79 board isn't supported, so I will still use the Arduino flashing device. However, I tried it out on a supported machine, and the reading part works definitely. The writing part I can't really tell because apparently that stick was also write protected. But if yours isn't write protected, then it's absolutely a viable option because the mainboard doesn't need to detect or fully detect changed or upgraded memory stick as long as there is a working one in it. So that means that you definitely can just upgrade your memory and then later on put it back into your computer, start up, change to your SPD and then be done with it, or you have to reboot, but you are done with it. You don't need to mess around with the Arduino flashing device. Another thing with the SPD-reader-Writer, what I said about reading it from your main board or without having to use external flashers, that's only for DDR3. When I'm making this video, or while I'm making this video, the update with DDR3 that you can read it from the main board has just been released while doing my video, so I fully expect that in the near future or whenever you're watching this video, probably there will be an update that you can read it from certain chipsets that support DDR4. The other option is Thaiphoon Burner. Thaiphoon Burner is actually paid software. You pay something like 21 euros when you pay in crypto, or like 30 if you pay by credit card. For the home version, something like that. I don't know. It's not too expensive if you plan to use it more than once, I guess. It's the same with as with the SPD reader and writer. If you have reversal software protection on your SPD chip, which is quite possible that you have it, then it's not guaranteed that you can write to it. In that case, if you don't want to change your chip, you can only edit the XMP profile, but not the first part of the SPD file. Anyways, its usage is fairly simple. Click read, then you get your dump. If you want to have a look at it here, you can see the file as such. Easy enough. Now, how to find out if your memory is actually protected or not? You can do it in Thaiphoon Burner. This would be EEPROM and then data protection check. Then you click check, and this check takes quite a bit of time. You have to let it run through, and then it will tell you which one is protected and what protection it has. And as you can see, it might report as crash, but you have to just let it run. It will work. And as you can see here, I have two unprotected sticks. These are the new ones, and I changed the chip. That's to be expected. And in bus 1 slot 0, there is a permanent software write protected chip on the first half of the SPD. That's the Kingston HyperX, and in that case I wouldn't be able to write to that part. If you want to use the SPD-reader-Writer, it's fairly similar. You have to connect here, and if you have a supported chipset, then you will find, you can click here, connect, then you can read. And after you have read it, you can check RSWP or check PSWP. In that case, you will get something similar to that. Now, while we're talking about Thaiphoon Burner, this is actually has an other very, very useful feature, and that is the SPD browser. Now, if you want to have a look at what other SPD files look like, maybe from your new chips, or if you want to tune yours, you have ample filter options here, and you can search for whatever chips or sticks that you want. Say, in my case, I wanted to have a look at this one. So you get like an overview, human readable overview, but you can also have a look at it. by clicking open, and now we have this SPD file that's from the parser that we just looked at. That's very useful, especially if you are unsure with like 1 bytes. Sometimes the documentation or your datasheet might be lacking, and in those instances it is super helpful to have a cheat sheet. And one of the best feature of Thaiphoon Burner is the SPD generator. Now in my case, because I don't have the license for it, I can't actually fully use it, but I guess it will work. So basically you can punch in whatever values that you want, SPD revision 1.1 and so on, and then it generates a SPD file for you. And the whole following part with how to edit and how to make these SPD files, while it's very useful to understand it and you can learn quite a bit from it, it's also bloody tedious. And if you can skip it, well, maybe you have to decide for yourself if it's worth $30 to you or not. But that brings us actually to the next part, and that is how to make these files. So what we actually need for that, we need the SPD design specification, and you can make an account with JEDEC and then you are able to download it. What you're looking for is this one here, the 21C solid state memory documents main page, something like that, or this title here, whatever. And that might look something like that. But I'm unfortunately not allowed to make this public. You can download it, perfectly legal from their site, but as far as I understood it, it's not allowed to share it publicly or even parts of it. So we won't do that. With that being said, the next best thing is this simtester.com DDR3 serial presence detect table. It's an article about the whole SPD, as you can see here. And it's super close to the original. It's actually very nicely written. And finally, we will also need the datasheet for your memory chips. In my case, it's this H5TC from SK Hynix. And since we have all these materials in place, we can actually start editing the SPD. So we can work through this document now. We start with byte 0, that's this one here. And the first one is always 92, it's the size of the SPD chip. And the H in this document always refers to that it's being a hex value, but you don't have to write that out. It's just for you to know that it's hex. So this is the Kingston dump from the 2GB sticks. So we started out, it's already 92, we can leave it at that. Byte 1, so this one here, is the SPD revision. And I will use the latest revision that's here. It's actually 1.3, but it doesn't really matter. So we use revision 1.2, and that is the hex value of 12 for byte 1. So we make a 2 out of this. Byte 2. What kind of memory it is. So DDR3 is always 0B. If you have DDR4, it's a different value, and it's a different value for DDR2, but we can leave it at 0B. Then byte 3 is what kind of memory we use. If it's registered, so server ECC memory, or is it unbuffered DIMM, and obviously we want an unbuffered. So that's 02, and we can leave it at that. Byte 4 is the SDRAM density and banks. So in my case, I have 8 internal banks per rank, and I have 2 ranks. So I have 16 chips divided by 2 ranks, so that's 8 banks per rank. If we then divide the total memory capacity, which is 8 GB, divided by 2 ranks, that's 4 GB, and 8 internal banks. So this one here, and we want to have 04. Byte 5, SDRAM and addressing, and now we have to look up the rows and columns of our new chips. So we go to the datasheet of our new chips, and then the easiest way to find that is search for row, and you will find a table, something like this. Obviously it will look different for different manufacturers, but yeah. And now we have to count the row and column addresses. If you remember, we have 8 banks times 512 megabytes. So we count the addresses, the row addresses, which is A0 to A15, and that's 16 addresses since A0 counts as an address. And the same with column, A0 to A9, that's 10 column addresses. We remember that value, go back, and then we look here, we have 512 megabyte chips, 16 rows and 10 columns. And we don't have the value for that here, unfortunately. And so what you can do is either look up a different memory stick, the SPD file of a different memory stick, or make the account with JEDEC, download the file, or you can search for it online. Yeah. In my case, I know that it's 21. Byte 6 is reserved, it's always 00, that's correct. Byte 7, module organization. We have 2 ranks and 8 chips. So we need to put in 09, and that's the same with the old memory stick, obviously, because that's defined by the PCB, but we can leave it at that. If you are not sure, you can look it up here. Byte 8, module memory bus width, that's 64 bits, and we don't have parity, otherwise it would be 72-bit for ECC memory, but we have 64 bits. You can, if you don't know it, you can look it up in the datasheet of your new chips. Probably will be and stay 64 bits. That's already in there, and that's correct. So now starting with byte 9 and onwards, basically from here, something like in this neighborhood, these are all timings, time bases stuff. And the easiest way I found to change that is either just blatantly copy it, or you can use a tool called SPD-editor GUI. I link it in the description, obviously. You can open that, and then I've saved a copy of this file here, and we open that. So file, this one here, and now we can change this value from this SPD editor here. First order of business, we want to change the frequency. Now this is 666 megahertz, so we want to change that to 800 in my case, since I'm going to use the 1600 speed bin, so 800 megahertz it is, and that changes some values. And for CLs that are supported, we have a look at the datasheet again. So we have 5, 6, 7, 8, 9, 10, and 11. So 5, 6, 7, 8, 9, 10, 11. We select that. We can also change some of the timings here. You will have to change that according to your data sheet and what kind of value you have here. There's no point in showing me, but it's basically just read it out and then TRP. So say for the TRP, it's 9. Here we have 13.75, so we have to up it until you have this value here, and so on and so on. I'm not going to show you that, you will find that out for yourself. When we're done, we save it, save as, and I will use new.bin, save, yes, I want to save. This is the old, that where we started. We were byte 9, and from here byte 9 you can see that there are quite a few differences. We can mark it, and then we can go through what it's different, and as you can see, it's quite a bit. So as I said, until here. Now the two values that also changed here are these two values here. These are the CRC. We don't care for them right now, but it's stopped here. what we can do now is have a look at it so far, what we have done with Thaiphoon. So we opened a new .bin in Thaiphoon, and we can see so far it worked out. This one we haven't touched it so far, also packed blah blah blah, but we can see that the total capacity is okay, the speed grade is okay. Now you can look at the timings, if they, I mean, this is very unoptimized and everything, but you can look if they are correct this way. And another representation of that we can have a look here. So the last value that's the SPD-editor GUI thingy altered was DRAM thermal refresh options. And now we can move forward. Next value that we have to look at is here, byte 16. So we can jump quite a bit ahead, but not so much. So byte 16, nominal height, if you want to change that, it's absolutely useless, but if you have to, here are the values. 61 is the thickness of the module, again, totally useless. Reference card, you can, so that's the thing is this one here, you can leave it at the value from the original dump, but the next really important part is byte 63. That's the address mapping from edge connector to DRAM. It's a bit convoluted title, but basically it's it asks if one of the RAMs is mirrored, and this value you have to look up from your original dump, which is this one here. It's 01. And we want to make sure that we have that in here as well, because that's determined from the PCB and not the chips that you are going to use. We can again skip quite a bit forward to here, and we can look it up what it is. It's byte 117. If we go back to the blog article, they also jump so this far. And module manufacturer ID code. Now, with this manufacturer ID code, how should I put it? The sad part is you can't just put any name in here that you like. So you can't make your own company or something like that. You have to look up, it's a lookup table. So basically the BIOS has a list, and with names that bought their place into this list from the JEDEC committee. So there are quite a few funny names. So you can call yourself King Kong or Strontium or Super PC Memory. If you're old school cool, then something like Cray. But I'm sure you're a law-abiding citizen and you're not an imposter, so we will change this value here to 0, or these two values actually, because it's this one and this one. And we will change them to 00, and that will give us an undefined name. So basically the name here won't be Kingston, it will be undefined. Then manufacturing location, we have no idea about that, so we can also zero it out. The next two values are week of the year and year. You don't have to convert anything to hex or so. So it's the year, we have 2022, and week, it's the 6th week. You can change that, so it's year 22, week 6. Module serial number. So this is actually quite a long one. It's from here, so byte 121 or 22, sorry, from here to here. So the original dump has like this one here. You can change that. Yeah, as it says here, there is no like definition how it should be made or made up, and you have to assign his own numbering system. You can I just blank it out because whatever. So we don't have a serial number. Then, as I said, these two values here are CRC. We leave them as they are, and we continue this value here, which is the part number. So the easiest way, so here you can be a bit creative. You can do your own module part number, and the number doesn't need to be a number. You can also add text here. So we could do something like this. You can use special characters. Not every program might be able to parse them correctly, yeah? But some of them are actually perfectly capable of using special characters. You just have to stay within a certain length. So the length can be here, maximum 18 digits. But within these 18 digits, you're actually free to use whatever you want. You can do it by hand, the conversion from ASCII to hex, or you can use like one of those online converter. It doesn't really matter. So in my case, put in something like that. Then you get the hex values that you have to input here. Or you can be lazy and leave it as is, or zero it out. Whatever you like. So we have this digit here is the last digit of the part number, and we've blanked it out. Next up, we have the module revision code, and that's again optional. I zeroed it out. Now we have done the module part. The next one is module revision code, manufacturer's ID code, and two manufacturer's ID codes. And these three values, I have no idea how you get them otherwise than just use it from okay, you could probably look it up on some JEDEC files. I have no idea where to find them. The easiest way I found is just rip them from another SPD. In my case, this would be 01, 00, 80 and 80. So these values give you the part number of the chips that you want to use. And as you can see here, that's the ones that I want to use, PBA. It's not strictly needed. You can leave it empty, and there is no part number. The important stuff is done. And that's really just about it when it goes to the SPD editing. Obviously, if you have a look at the dump, there is a lot of optimization that can be done. I've done it very crudely for this demonstration, especially with the timings. There is definitely some work that can be done. You can also add an XMP profile. This is probably the easiest with the Thaiphoon Burner, but you can also just look up other modules that have an XMP profile. In my case, if you want to add an XMP profile, I have the dumps of another Kingston module that I own, HyperX something, I don't know. I'll show it in a picture. But here is like an example of an XMP profile that you could implement. So we have here the last values that we changed beforehand, and then you have the XMP profiles here that can be edited. But it's not strictly needed. But again, if you want to do it for yourself, you probably want to spend a little bit more time and do some optimization, and why not add an XMP profile while you're at it. Yeah, and that's more or less about it when it comes to making your own SPD file. The best resources that I've found is obviously this SimTester website, really cool blog posts, but also if you can download SPD JEDEC specifications, because nothing beats the original source. So let's talk about the flashing. As I pointed out earlier, we need this to circumvent the permanent software write protection, PSWRP. But basically, we have an Arduino. We need some optocouplers, resistors, capacitor here, that's optional, but I would recommend using it. I did it on a perf board because, well, connections are a little bit better. It doesn't really look nice, I agree, but it's better. You don't get like loose connections like with when you do it on a breadboard.
As it's stated here, there are optional parts that we won't use. One of the optional parts is SA2 control and SA0 control. These are optional. I won't, just straight up won't connect this. We can forget about these ones. Now with the high voltage source, you can do it with a boost converter as here, but it's actually easier to, or you don't need extra components if you just use a battery. So I did that. Now with these, we hook it up. Like in the schematics, I use more or less the same values for the resistors and capacitor. The only really important values are these here. These should be just that for the voltage divider, because otherwise you get too high of a voltage and then the Arduino is not happy. Talking about Arduino not being happy, the reason we have to use these optocouplers is, as you can see here, to circumvent the write protection, we need a higher voltage of 9 volts. And the Arduino is super unhappy if you apply more than 5 volts to any of the I/O pins. This will definitely damage the Arduino, and that's the reason why we need these optocouplers. An optocoupler is basically a switch that is actuated by a diode or a LED internally, and that turns on the switch here. And in this way we can separate the higher voltage from the lower voltage on the. I added a switch to disconnect the 9 volt from the battery from the rest of the circuit. This is absolutely optional. You don't need to do that. Now, when we look at these connections here to the memory or the SPD chip on the memory, there are several options that you can look at. One is desolder the chip and directly solder the wires to the chip, which is a bit harder since they are quite small. Another option is to solder to the pads on the PCB. That's what I did. And the third option is to use these fingers here. And personally, I didn't want to solder to these pads because it doesn't look clean or nice, but it's definitely possible. It's also possible that you can buy like a DDR whatever socket and then solder to the pins of that socket. If you want to do this on a regular base, this might be interesting to you. Personally, I don't plan to do this on a daily basis, so I'm happy with more work when you have to solder to the PCB. The upside for soldering to the PCB is you can remove it and then you won't see it. It's pretty clean compared to have solder residue on the pads here. But it's an optical problem. If you have it in the socket, you won't see it. It won't interfere with the operation of the DIMM at all. So if you're happy with having messed up pads, whatever, do it. No worries.
The first step that we want to take is actually open the firmware in the Arduino IDE. You can see this is the firmware, but we don't have to do anything in this one here. What you want to make sure is that you also opened the settings.h file. And in here, if you build it according to the schematics from the project description, you don't need to change anything here. If you use, say, a different Arduino Uno or whatever, you might need to change the pin config here. These are the pin numbers you want to reflect what you have used in your project. And then if you used standard config, you can leave it, otherwise you have to change it. And if we have done that, we can first check that we have the correct processor or Arduino board. In my case, it's an Arduino Nano. And they come in 2 flavors, or actually 3 if you count the old bootloader, but the 328p or 168. And I have a 168, so we set that, and after that we can define the port where the Arduino is connected to, and then we can apply that, and after that we can hit the upload button and wait until the upload is done. And when that is done, the Arduino is flashed and ready to be used. So after we have successfully connected the Arduino with the SPD chip, we can first check out if on the Arduino side everything is fine. And for that we can open the serial monitor. If you get a reply like a exclamation mark, everything works on the Arduino side of things. So we can close it. And we can open the SPD-reader-Writer GUI. Now on the first startup, you might have to configure the devices. I can't really remember, but you will figure it out. After that we can connect it. In my case it's COM6 connect. As you can see, COM6 is ready. So let's start. First we want to read. This is what we get. Now we want to save it, obviously. Now we have saved it. With my Kingston stick, I cannot write to it. So if I try to write this to it, partially or fully write protected, it doesn't work. That's what I said earlier. These chips are completely locked down. Trying to write, nothing written to, could not write. Try if the clear RSWP changes something, but it doesn't. So as I said, in this case, you have to buy a replacement chip or live with the fact that you only can write to like from here to here or from here onwards, but not the top part or the top 128 bits, I think. But let's assume that you can write to it, so we can drag it in here. And as you can see here, CRC is bad. And this CRC is a checksum. It's a simple function that actually checks if the values that have been written or have been read by the BIOS are transmitted without an error, so that the values are correct. This is a checksum of the first part of the SPD. We have to fix it before we can flash it. And how to do that is go to Edit, Fix CRC. CRC has been corrected. So you can see here, it's changed these values. And now we would be ready to flash it. It would be done with this here. And if you have a working chip, you won't get this error message. I set up a rig where the chipset is supported. It's an old first gen i5 or something like that. And I want to show you here how to use SPD-reader-Writer when you don't have a flashing device, but rather use the built-in flashing over the mainboard, basically. And for that we want to start the SPD-reader-Writer GUI in as an administrator. Then we can go connect. And here you can select the chipset as a flashing device. We connect. We connect and now we can read. We have to specify the EEPROM device. In my case it's 82. And this is the SPD of a 16GB unbuffered ECC stick that we just read here. Now the writing part would be pretty much the same as with the Arduino flasher. You load the file and then hit write to. And you again have to select the EEPROM device that you want or need to use. But what if your computer isn't able to boot if the memory stick is installed? In my case, this was the case with the 16GB unbuffered DIMM. The mainboard just wouldn't boot with that stick installed. And in that case, what you can do is basically remove the stick or just a little bit and then wait until the system has posted and then reinsert the stick into the PC so that the stick isn't present when posting. But you can edit afterwards. You have to be a little bit careful. Just make sure that you put it in straight, not at an angle, so you don't short out stuff that shouldn't be shorted out. But it should work, or it did work in my case, as you can see in the pictures. And that's about it. I hope this was helpful to you. If you have questions, you can leave them in the comments. I'll do my best to answer them. And yeah, have a nice day. Bye bye.